The hidden highways beneath our feet. Beneath the roaring crowds in packed stadiums, beneath city streets and ocean floors, lies a secret parallel internet, an invisible network of dormant potential called dark fiber. Picture millions of miles of unused glass threads, silently coiled in conduits worldwide, waiting to be awakened. These are the uncontested superhighways of data, capable of transmitting information at nearly the speed of light with unmatched security. In this video, we'll unravel how this buried infrastructure powers everything from 5G revolutions to AI-driven cities, and why stadiums, those temples of human connection, are becoming nerve centers for a bandwidth revolution you never see coming. Dark fiber refers to unused strands of fiber optic cable, initially laid in bulk by telecom companies who anticipated future demand. Since installing physical cable is exponentially more expensive than producing the fiber itself, it made economic sense to deploy extra capacity. Today, organizations lease or buy these dark strands to build private optical networks, giving them total control over speed, security, and data protocols. Unlike traditional broadband, dark fiber isn't shared or throttled. It's a dedicated pipeline where you decide the rules. The market is exploding. Valued at $3.74 billion in 2024, projections show it could hit $11.94 billion by 2032, growing at a staggering 16% annually. This surge is fueled by insatiable demands, cloud computing sprawl, data center proliferation, and crucially, the rise of 5G. Fifth-generation mobile networks require near-zero latency and colossal bandwidth. Dark fiber provides the perfect backhaul to link cell towers to core networks, enabling real-time miracles like remote surgery and autonomous vehicles. Without these light-speed conduits, 5G's promise evaporates. Now consider stadiums. Modern arenas are data monsters. Thousands of fans stream HD video, IoT devices monitor everything from concession sales to security cameras, and broadcasters demand flawless live feeds. Here, dark fiber shines. It can carry hundreds of uncompressed HD video streams with predictable microsecond latency. Innovative production companies now ditch bulky broadcast trucks, routing feeds directly via dark fiber to remote studios, slashing costs while enabling cinematic multi-angle replays. The fiber web beneath stadiums ensures your phone connects instantly during a touchdown, and that security systems operate flawlessly. But what about that intriguing phrase, a global shadow simulation? While dark fiber security and isolation make it ideal for running large-scale segregated simulations, there's no evidence of a clandestine global network operated from stadiums. Academic tools such as the Shadow Network Simulator do exist, allowing researchers to model complex systems in private fiber environments. However, the real magic isn't secrecy, it's capability. Dark fiber scalability lets users light new capacity instantly by upgrading hardware. Its physical isolation thwarts eavesdropping, and its low latency is irreplaceable for AI training or financial trading. For businesses, it's a long-term strategic asset. No more begging providers for bandwidth, just pure, unimpeded data flow. As edge computing and AI explode, these hidden highways will become the circulatory system of tomorrow's digital world, starting beneath the very grounds where we cheer today. Lighting the dark. From stadiums to silicon brains. But how do we transform these inert glass threads into intelligent conduits capable of reshaping industries? The answer lies in lighting the fiber. a process as revolutionary as flipping a switch in a dormant power plant. At each end of a dark fiber strand, organizations deploy optical transceivers, devices that convert electrical data signals into pulses of laser light. These photons race through the fiber's core via total internal reflection, bouncing off ultra-pure silica walls with minimal signal loss over hundreds of miles. To amplify capacity without laying more cable, engineers use wavelength division multiplexing. This technique splits light into multiple lanes on a single strand, like sending thousands of colored laser beams down the same tunnel without interference. A single fiber can thus carry over 80 terabits per second, enough to transmit the entire Library of Congress in under 2 seconds. The activation cost? Far lower than deploying new cable. Stadium operators can light dark fiber for critical events by renting portable fiber huts housing compact hardware, scaling bandwidth on demand during a Super Bowl or World Cup final. This technical alchemy enables stadiums to function as hyper-connected data fortresses. Consider Levi Stadium in California. Beneath its turf, 400 miles of dark fiber form a private optical mesh. During games, 70,000 fans generate a data deluge. 40,000 mobile devices, 2,000 wireless access points, and 4K cameras capturing every angle. Dark fiber's dedicated lanes ensure zero buffering for live TikTok streams, while simultaneously ferrying terabytes of biometric data from wearables to cloud AI. Security teams leverage this in real time. Facial recognition algorithms scan 50 faces per second across 400 cameras, instantly cross-referencing against databases via dark fiber's encrypted pathways. Even concessions transform. IoT sensors on soda fountains relay inventory levels to regional distribution centers, triggering automatic restocking when syrup runs low. This operational symphony hinges on dark fiber's sub-millisecond latency, a 200x improvement over copper cables, ensuring that when a goal line sensor detects a touchdown, the replay hits jumbotrons before the cheers subside. Beyond the roar of crowds, dark fiber's true disruption emerges in high-stakes domains demanding absolute reliability. In finance, Wall Street firms lease dark fiber strands between New York and Chicago, shaving 3 milliseconds off trade execution times, a delay worth $100 million annually to high-frequency traders. Healthcare pioneers like Johns Hopkins use dark fiber backbones for telesurgery networks, where a lag exceeding 10 milliseconds could prove fatal. Surgeons in Baltimore guide robots performing operations in Nairobi, with haptic feedback and 8K imaging flowing over dedicated wavelengths immune to public internet congestion. Meanwhile, tech giants deploy dark fiber for AI's voracious appetites. Training models like GPT-5 requires moving petabytes between data centers. Public cloud links risk throttling or interception, but dark fiber's isolated channels let Meta or Google shift exabytes of training data with military-grade security. Physical isolation matters. Since signals never escape the fiber, hackers can't tap them without physically accessing the cable, a near impossible feat in armored underground conduits. This brings us to the shadow simulation enigma. While no evidence supports dystopian global constructs, dark fiber's segregated nature makes it ideal for running massive, real-world simulations requiring airtight data integrity. Take Project Olympus at MIT. Researchers use a dark fiber ring to simulate entire power grids, modeling cascading blackouts under cyber attack scenarios. By walling off the simulation from the public internet, they prevent malicious actors from probing or distorting results. Similarly, epidemiologists at the CDC employ dark fiber networks to run pandemic spread models with billions of variables, incorporating live airport transit data without risking leaks of sensitive travel patterns. Even autonomous vehicle developers leverage this. Waymo operates private dark fiber loops between testing facilities where thousands of self-driving cars share sensor data in a closed-loop shadow world to simulate rare edge cases like blizzards or pedestrian swarms without real-world risks. These simulations aren't secret societies. They're high-fidelity digital twins thriving on dark fiber's unique trifecta: limitless scalability, uncompromised security, and light-speed synchronization. As we stand at this inflection point, dark fiber evolves from passive infrastructure to the central nervous system of emergent technologies. Edge computing, where data is processed near its source, demands dark fiber spines to connect microdata centers in stadium basements or factory floors. Smart cities like Singapore already deploy municipal dark fiber grids linking traffic cameras, environmental sensors, and emergency systems into a unified AI brain that predicts accidents or pollution spikes. The next leap? Quantum networking. Dark fiber strands are being optimized to transport quantum-entangled photons, enabling hack-proof communication for banks and governments. What began as unused cable beneath our feet now underpins humanity's most ambitious experiments, from simulating galaxies to orchestrating the metaverse. And as you stream this video, remember, the same hidden threads that deliver cat videos are quietly powering revolutions you'll only notice when they change the world.